designing a deployment strategy for AWS using ECS, S3, EFS, and RDS services. An overview of several AWS-specific hooks and operators. Demonstrating how to use AWS-specific hooks and operators with a use case. After our brief introduction in the previous chapter, this chapter will dive further into how to deploy and integrate Airflow with cloud services in Amazon AWS. First, we'll start by designing an Airflow deployment by mapping the different components of Airflow to AWS services. Then we'll explore some of the hooks and operators that Airflow provides for integrating with several key AWS services. Finally, we'll show how to use these AWS-specific operators and hooks to implement a use case for generating movie recommendations. Section 16.1. Deploying Airflow in AWS. In the previous chapter, we described the different components that comprise an Airflow deployment. In this section, we'll design a few deployment patterns for AWS by mapping them to specific AWS cloud services. This should give you a good idea of the process involved in designing an Airflow deployment for AWS and provide a good starting point for implementing one. Section 16.1.1. Picking cloud services. Starting with the Airflow web server and scheduler components, one of the easiest approaches for running these components is probably Fargate, AWS's serverless compute engine for containers. One of the main advantages of Fargate, compared to other AWS services like ECS or EKS, is that it allows us to easily run containers in AWS without having to worry about provisioning and managing the underlying compute resources. This means we can simply provide Fargate with a definition of our web server and scheduler container tasks, and Fargate will take care of deploying, running, and monitoring the tasks for us. Footnote 1. Elastic Compute Service, similar to Fargate but requires you to manage the underlying machines yourself. Footnote 2. Elastic Kubernetes Service, AWS's managed solution for deploying and running Kubernetes. For the Airflow Metastore, we recommend looking toward AWS's hosted RDS solutions, for example, Amazon RDS, which helps with setting up relational databases in the cloud by taking care of time-consuming administration tasks, such as hardware provisioning, database setup, patching, and backups. Amazon RDS provides several types of RDS engines you can choose from, including MySQL, Postgres, and Aurora, which is Amazon's proprietary database engine. In general, Airflow supports using all of these backends for its Metastore, so your choice may depend on other requirements, such as cost or features such as high availability. Footnote 3. Amazon RDS includes several database types, such as PostgreSQL, MySQL, and Aurora. AWS provides several options for shared storage. The most prominent is S3, a scalable object storage system. S3 is generally great for storing large amounts of data with high durability and availability for a relatively low cost. As such, it is ideal for storing large datasets, which we may be processing in our DAGs, or storing temporary files, such as the Airflow worker logs, which Airflow can write to S3 natively. A drawback of S3 is that it cannot be mounted as a local file system into the web server or scheduler machines, making it less ideal for storing files such as DAGs, which Airflow requires local access to. In contrast, AWS's EFS storage system is compatible with NFS and can therefore be mounted directly into Airflow containers, making it suitable for storing DAGs. EFS is, however, quite a bit more expensive than S3, making it less ideal for storing data or our log files. Another drawback of EFS is that it is more difficult to upload files into EFS than S3, as AWS does not provide an easy web-based or CLI interface for copying files to EFS. For these reasons, it may still make sense to look to other storage options such as S3, or alternatively Git, for storing DAGs, and then use an automated process to sync the DAGs to EFS, as we will see later in this chapter. Overall, this gives us the following setup. Figure 16.1. Fargate for the compute components, Airflow web server and scheduler. Amazon RDS, for example Aurora, for the Airflow Metastore, S3 for storage of logs and optionally also for data, EFS for storage of DAGs. Section 16.1.2, Designing the Network. We also need to consider how these services will be connected and how we can manage internet access to Airflow. A typical AWS networking setup is to create a VPC, Virtual Private Cloud, containing both public and private subnets. In this type of setup, the private subnets inside the VPC can be used for services that should not be exposed directly to the internet, while the public subnets can be used to provide external access to services and outgoing connectivity to the internet. We have a couple of services that need to be connected by network for our Airflow deployment. For example, both the web server and scheduler containers need to have access to the Airflow Metastore RDS and EFS for retrieving their DAGs. We can arrange this access by connecting both containers, the RDS and our EFS instance, to our private subnet, which will also ensure that these services are not directly accessible from the internet. Figure 16.2. To provide access to S3 for our containers, we can also place a private S3 endpoint within the private subnet, which will ensure that any S3-bound traffic doesn't leave our VPC. We also want to expose our Airflow web server to the internet, with the proper access controls, of course, so that we can access the web server from our workspace. A typical approach is to place them behind an application load balancer, ALB, which is publicly accessible in the public subnet via an internet gateway. This ALB will handle any incoming connections and forward them to our web server container if appropriate. To make sure that our web server can also send back responses to our requests, we also need to place an NAT gateway in the public subnet. Section 16.1.3, Adding DAG Syncing. As mentioned before, a drawback of using EFS for storing DAGs is that EFS is not very easy to access using web-based interfaces or command line tools. As such, you may want to look towards setting up a process for automatically syncing DAGs from another storage backend, such as S3 or a Git repository. One possible solution is to create a Lambda function that takes care of syncing DAGs from Git or S3 to EFS. Figure 16.3. This Lambda can be triggered either by S3 events or a build pipeline in the case of Git to sync any changed DAGs to EFS, making the changes available to Airflow. Section 16.1.4, Scaling with Celery Executor. Although this setup should be robust enough to handle many workloads, we can improve the scalability of our Airflow deployment by switching to the Celery Executor. The main advantage of this switch is that the Celery Executor allows you to run each Airflow worker in its own container instance, thus substantially increasing the resources available to each worker. To use the Celery Executor, we have to make a number of changes to our design, figure 16.4. First, we need to set up a separate pool of Fargate tasks for the Airflow workers, which run in separate processes in the Celery-based setup. Note that these tasks also need to have access to the Airflow Metastore and the logs bucket to be able to store their logs and results. Second, we need to add a message broker that relays jobs from the scheduler to the workers. Although we could choose to host our own message broker, for example, RabbitMQ or possibly Redis, in Fargate or something similar, it is arguably easier to use AWS's SQS service, which provides a simple serverless message broker that requires little effort to maintain. Of course, a drawback of using the Celery Executor is that the setup is a bit more complex than the local executor, and therefore requires more effort. The added components, most notably the extra worker tasks, may also add some considerable costs for the extra compute resources required for each worker. Section 16.1.5, Further Steps. Although we have sketched some basic deployment strategies for Airflow in AWS, we should be careful to note that these setups should not be considered production ready, as we still need to consider a number of factors. First and foremost, security is an important consideration for production deployments. Although we have put some effort into shielding our different components from the public internet, we still need to consider further restricting access to components using security groups and network ACLs, limiting access to AWS resources using the appropriate IAM roles and policies, and so on. At the Airflow level, you should also consider how you would like to secure Airflow, using Airflow's RBAC mechanism, etc. Footnote 4. Identity and Access Management. We would also expect production deployments to have a robust approach for logging, auditing, and tracking metrics, and for raising alerts if issues are encountered with any of the deployed services. For this, we recommend looking at the corresponding services provided by AWS, including CloudTrail and CloudWatch. Section 16.2. AWS-specific hooks and operators. Airflow provides a considerable number of built-in hooks, operators, that allow you to interact with a great number of the AWS services. These allow you to, for example, coordinate processes involving moving and transforming data across the different services, as well as the deployment of any required resources. For an overview of all the available hooks and operators, see the Amazon AWS Provider Package. Footnote 5. Can be installed in Airflow 2 using the Apache-Airflow-Providers-Amazon Providers package, or in Airflow 1.10 using the backport package Apache-Airflow-Backport-Providers-Amazon. Due to their large number, we won't go into any details of the AWS-specific hooks and operators, but rather refer you to their documentation. However, tables 16.1 and 16.2 provide a brief overview of several hooks and operators with the AWS services they tie into and their respective applications. A demonstration of some of these hooks and operators is also provided in the next section. One hook that deserves special mention is the AWS Base Hook, which provides a generic interface to AWS services using AWS's BOTO3 library. To use the AWS Base Hook, instantiate it with a reference to an Airflow connection that contains the appropriate AWS credentials. The required connection can be created in Airflow using the Web UI, figure 16.5, or other configuration approaches, for example, environment variables. The connection essentially requires two details: an access key and secret that point to an IAM user in AWS. Footnote 6. We'll provide an example of how to obtain these details in the next section. Once we have instantiated the hook, we can use it to create BOTO3 clients for different services using the get_client_type method. For example, you can create a client for the AWS Glue service as follows. With this client, we can perform all kinds of operations on the Glue service in AWS. For more details on the different types of clients and the supported operations, you can reference the BOTO3 documentation here. To be able to perform any of these operations, the hook's IAM user used should have the appropriate permissions in AWS. As such, make sure to assign the appropriate permissions to the respective user using IAM policies. In the next section, we'll show an example of building a custom operator based on the AWS Base Hook, which demonstrates how this all ties together. Section 16.3. Use Case: Serverless Movie Ranking with AWS Athena. To explore some of these AWS-specific features, let's turn to a small example. Section 16.3.1. Overview. In this example, we're interested in using some of the serverless services in AWS, S3, Glue, Athena, to analyze the movie data we encountered in previous chapters. Our goal is to find the most popular movies by ranking them by their average rating, using all the ratings up to that point in time. One of the advantages of using serverless services for this task is that we don't have to worry about running and maintaining any servers ourselves. This makes the overall setup relatively cheap. We only pay for things while they're running, and it requires relatively low maintenance. To build this serverless movie ranking process, we need to implement a couple of steps. First, we fetch the movie ratings from our API and load them into S3 to make them available in AWS. We plan to load the data on a monthly basis so that we can calculate the ratings for each month as new data comes in. Second, we use AWS Glue, a serverless ETL service, to crawl the ratings data on S3. By doing so, Glue creates a table view of the data stored in S3, which we can subsequently query to calculate our rankings. Finally, we use AWS Athena, a serverless SQL query engine, to execute an SQL query on the ratings table to calculate our movie rankings. The output of this query is written to S3 so that we can use the rankings in any applications downstream. This provides us with a relatively straightforward approach, figure 16.6, for ranking movies, which should scale easily to large datasets, as S3 and Glue Athena are highly scalable technologies. Moreover, the serverless aspect means that we don't have to pay for any servers to run this one-in-a-month process, keeping down costs. Nice, right? Section 16.3.2, Setting up Resources. Before implementing the DAG, let's start by creating the required resources in AWS. Our DAG will require the following cloud resources: an S3 bucket that will contain our ratings data, a second S3 bucket that will store the ranking results, a Glue crawler that will create a table from our ratings data, an IAM user that will allow us to access the S3 buckets and call services such as Glue and Athena. One way to configure these resources is to open the AWS console here and create the required resources manually in the respective sections of the console. However, for sake of reproducibility, we recommend defining and managing your resources using an infrastructure as code solution, such as CloudFormation, AWS templating solution for defining cloud resources in code. For this example, we have provided a CloudFormation template that creates all of the required resources in your account. For brevity, we will not dive into the details of the template here, but happily refer you to its details online. See this link. To create the required resources with our template, open the AWS console, go to the CloudFormation section, and click Create Stack, figure 16.7. On the following page, upload the provided template and click Next. On the Stack Details page, enter a name for your stack, equals this set of resources, and fill in a unique prefix for your S3 bucket names, which is required to make them globally unique. Now, click Next a few more times, making sure to select I acknowledge that AWS CloudFormation might create IAM resources with custom names on the review page, and CloudFormation should start creating your resources. Once complete, you should be able to see the status of the created stack in the CloudFormation Stack Overview page, figure 16.8. You can also see which resources CloudFormation created for you under the Resources tab, figure 16.9. This should include an IAM user and a bunch of access policies, the two S3 buckets, and our Glue crawler. Note that you can navigate to the different resources by clicking the physical ID link of each resource, which will navigate to the respective resource in the corresponding section of the AWS console. If something went wrong during the creation of the stack, you can try identifying the issue using the Events in the Events tab. This can happen if, for example, your bucket names conflict with someone else's pre-existing buckets, as they must be globally unique. Once we have our required set of resources, we have one thing left to do. To be able to use the IAM user the stack in our DAG created, we need to create an access key and secret for the user that can be shared with Airflow. To create this access key and secret, scroll down until you find the AWS:IAM:user resource created by the stack and click its physical ID link. This should bring you to the user overview in AWS's IAM console. Next, navigate to the Security Credentials tab and click Create Access Key, figure 16.10. Write the generated access key and secret down and keep them secure, as we'll need this later in Airflow. Section 16.3.3, Building the DAG. Now we have all the required resources, let's start implementing our DAG by looking for the appropriate hooks and operators. For the first step, we need an operator that fetches data from our Movie Ratings API and uploads them to S3. Although Airflow provides a number of built-in S3 operators, none of them allows us to fetch ratings from our API and upload them directly to S3. Fortunately, we can also implement this step by combining the Python operator and the S3 hook. Together, these classes allow us to fetch the ratings using our own Python function or functions, and then upload the results to S3. Note that the S3 hook requires a connection ID that specifies which connection, that is, which credentials, to use for connecting to S3. As such, we need to make sure that Airflow is configured with a connection that has an access key and secret for a user with sufficient permissions. Fortunately, we already created such a user in the previous section, using our CloudFormation stack, and can now use the credentials to create our Airflow connection, figure 16.5. After creating the connection, make sure to substitute its name and the name of your S3 bucket under the op_quargs argument to the Python operator. For the second step, we need an operator that is able to connect to AWS to trigger our Glue crawler, which was also created by the CloudFormation stack. Unfortunately, Airflow does not provide an operator for this operation, meaning we have to build our own. However, we can use the built-in AWS base hook as a base for our operator, which provides us with easy access to the different AWS services using BOTO3. Using this AWS base hook, we can create our own operator, the Glue Trigger Crawler operator, that essentially retrieves a Glue client using the AWS base hook and uses it to start our crawler using the Glue client's start_crawler method. After checking if the crawler started successfully, we can check the status of the crawler using the client's get_crawler method, which, among other things, returns the status of the crawler. Once the crawler reaches the ready state, we can be fairly confident that it has finished running, meaning we can continue with any downstream tasks. Altogether, an implementation of this operator could look something like the following. Footnote 7. See Chapter 8 for more details on creating custom operators. Footnote 8. This example could arguably be made more robust by adding more checks for unexpected responses, statuses, and so on. We can use Glue Trigger Crawler operator as follows. Finally, for the third step, we need an operator that allows us to execute a query in Athena. This time we're in luck, as Airflow provides an operator for doing so, the AWS Athena operator. This operator requires a number of arguments: the connection to Athena, the database, which should have been created by the Glue crawler, the execution query, and an output location in S3 to write the results of the query to. Altogether, our usage of the operator would look something like this. Now that we have created all the required tasks, we can start tying everything together in the overall DAG. With everything in place, we should now be able to run our DAG within Airflow, figure 16.11. Assuming everything is configured correctly, your DAG runs should be successful and you should see some CSV outputs from Athena appearing in your ratings output bucket, figure 16.12. If you run into issues, make sure that the AWS resources were set up correctly and that your access key and secret were configured correctly. Section 16.3.4, Cleaning Up. After finishing with this example, make sure to clean up any resources you created in AWS to avoid incurring any unnecessary costs. If you used our CloudFormation template for creating the resources, you can delete most by deleting the stack. Note that some resources, like the S3 buckets, will have to be removed manually, even if you are using the template, as CloudFormation will not let you delete non-empty buckets automatically. Make sure to check if all created resources were deleted successfully, paying extra attention to check any resources you may have created manually. Summary. Airflow can be deployed in AWS using services such as ECS, Fargate for running the scheduler and web server processes, EFS S3 for storage, and Amazon RDS for the Airflow Metastore. Airflow provides many AWS-specific hooks and operators that allow you to integrate with different services with the AWS Cloud Platform. The AWS Basehook class provides low-level access to all services in AWS using the BOTO3 library, allowing you to implement your own high-level hooks and operators if these do not yet exist. Using AWS-specific hooks and operators generally requires you to configure the required resources and access permissions in AWS and Airflow so that Airflow is allowed to perform the required operations. Chapter 17, Airflow on Azure. This chapter covers designing a deployment strategy for Azure, an overview of several Azure-specific hooks and operators, demonstrating how to use Azure-specific hooks and operators with a use case. This chapter will dive further into how to deploy and integrate Airflow with cloud services in the Microsoft Azure cloud. First, we'll start designing an Airflow deployment by mapping the different components of Airflow to Azure services. Then we'll explore some of the hooks and operators that Airflow provides for integrating with several key Azure services. Finally, we'll show how to use these Azure-specific operators and hooks to implement a use case for generating movie recommendations. Section 17.1, Deploying Airflow in Azure. In Chapter 15, we described the different components comprising an Airflow deployment. In this section, we'll design a few deployment patterns for Azure by mapping them to specific Azure cloud services. This should give you a good idea of the process involved in designing an Airflow deployment for Azure and provide a good starting point for implementing one. Section 17.1.1, Picking Services. Let's start with the Airflow web server and scheduler components. One of the easiest approaches for running these components is to use Azure's managed container services, such as Azure Container Instances, ACI, or Azure Kubernetes Service, AKS. However, for the web server, we also have another option, the Azure App Service. Azure App Service is, as Microsoft puts it, a fully managed platform for building, deploying, and scaling your web apps. In practice, it provides a convenient approach for deploying web services onto a managed platform that includes features such as authentication and monitoring. Importantly, App Service supports deploying applications in containers, which means that we can use it to deploy the Airflow web server and allow it to take care of authentication for us. Of course, the scheduler doesn't need any of the web-related functionality provided by App Service. As such, it still makes sense to deploy the scheduler to ACI, which provides a more basic container runtime. For the Airflow Metastore, it makes a lot of sense to look toward Azure's managed database services, such as Azure SQL Database. This service effectively provides us with a convenient solution for a relational database on an SQL server, without having to worry about the maintenance of the underlying system. Azure provides a number of different storage solutions, including Azure File Storage, Azure Blob Storage, and Azure Data Lake Storage. Azure File Storage is the most convenient solution for hosting our DAGs, as file storage volumes can be mounted directly into the containers running in App Service and ACI. Moreover, file storage is easy to access using supporting user applications, such as the Azure Storage Explorer, making it relatively straightforward to add or update any DAGs. For data storage, it makes more sense to look toward Azure Blob or Data Lake Storage, as these are better suited for data workloads than file storage. This gives us the following setup, also shown in Figure 17.1. App Service for the Airflow web server. ACI for the Airflow scheduler. Azure SQL Database for the Airflow Metastore. Azure File Storage for storing DAGs. Azure Blob Storage for data and logs. Section 17.1.2, Designing the Network. Now we have picked services for each component, we can start designing the networking connectivity between them. In this case, we want to expose the Airflow web server to the internet so that we can access it remotely. However, we want to keep other components, such as the Airflow Metastore and the Airflow Scheduler, in a private network to avoid exposing them online. Fortunately, the Azure App Service makes it easy to expose the web server as a web application. This is exactly what it is designed for. As such, we can let App Service take care of exposing the web server and connecting it to the internet. We can also use the built-in functionality of App Server to add a firewall or an authentication layer, which can be integrated with Azure AD, etc., in front of the web service, preventing unauthorized users from accessing the web server. For the scheduler and Metastore, we can create a virtual net, VNet, with a private subnet and place these more private components inside the private network, figure 17.2. This will provide us with connectivity between the Metastore and the scheduler. To allow the web server to access the Metastore, we need to enable VNet integration for App Service. Both Azure File Storage and Azure Blob Storage can be integrated with App Service and ACI. By default, both these storage services are accessible via the Internet, meaning that they don't need to be integrated into our VNet. However, we also recommend looking into using private endpoints for connecting storage accounts to your private resources, which provides more security by ensuring that data traffic does not traverse the public Internet. Section 17.1.3, Scaling with the Celery Executor. Similar to the AWS solution, we can improve the scalability of our Azure deployment by switching from the local executor to the Celery executor. In Azure, switching executors also requires us to create a pool of Airflow workers that the Celery executor can use. As we are already running our scheduler and ACI, it makes sense to create the extra Airflow workers as additional container services running in ACI, figure 17.3. Next, we also need to implement a message broker for relaying jobs between the scheduler and the workers. Unfortunately, there are, to our knowledge, no managed solutions in Azure that integrate well with Airflow for this purpose. As such, the easiest approach is to run an open source service in ACI that can function as a message broker for Airflow. Open source tools such as RabbitMQ and Redis can be used for this purpose. Section 17.1.4. Further steps. Although this illustrates some basic deployment strategies for Airflow in Azure, we should be careful to note that these are not production-ready. Similar to the AWS designs, any production-ready setup will still need to take extra steps, such as setting up proper firewalls and access controls. At the Airflow level, you should also consider how you want to secure Airflow, for example, using Airflow's RBAC mechanism, etc. We also expect production deployments to have a robust approach for logging, auditing, tracking metrics, and raising alerts if issues are encountered with any of the deployed services. For this, we recommend looking at the corresponding services provided by Azure, including Azure Log Analytics, App Insights, and so on. Section 17.2, Azure-specific hooks, operators. At the time of writing this book, Airflow has relatively few built-in hooks and operators specific for Azure cloud services. This probably reflects a bias of the Airflow community. However, it should be pretty straightforward to implement and contribute your own using the Azure Python SDK. Additionally, several services can be accessed using more generic interfaces, for example, ODBC, as we will see in the example use case, meaning that Airflow can still interact well with Azure cloud services. Airflow's Azure-specific hooks and operators, tables 17.1 and 17.2, are provided by the Microsoft Azure Provider Package. Several of these hooks and operators can be used to interact with Azure's different storage services, for example, Blob, FileShare, and Data Lake storage, with additional hooks providing access to specialized databases, for example, Cosmos DB, and container runtimes, for example, Azure Container Service. Footnote 2. Can be installed in Airflow 2 using the Apache-Airflow-Providers-Microsoft-Azure Providers package, or in Airflow 1.10 using the backport package Apache-Airflow-Backport-Providers-Microsoft-Azure. Section 17.3. Example. Serverless movie ranking with Azure Synapse. To get familiar with using some Azure services within Airflow, we'll implement a small movie recommender using several serverless services, similar to the AWS use case, but now applied to Azure. In this use case, we're interested in identifying popular movies by ranking them based on their user average rating. By using serverless technologies for this task, we hope to keep our setup relatively simple and cost-effective by not having to worry about running and maintaining any servers, but letting Azure take care of this for us. Section 17.3.1 Overview. Although there are probably many different ways to perform this kind of analysis in Azure, we will focus on using Azure Synapse for performing our movie ranking, as it allows us to perform serverless SQL queries using its SQL on-demand capability. This means we only have to pay for the amount of data we process in Azure Synapse, and don't have to worry about running the costs and maintenance of the compute resources it uses. To implement our use case using Synapse, we need to perform the following steps. 1. Fetch ratings for a given month from our Ratings API and upload the ratings into Azure Blob Storage for further analysis. 2. Use Azure Synapse to execute an SQL query that ranks our movies. The resulting list of ranked movies will be written back to Azure Blob Storage for further downstream consumption. This gives us the data process shown in Figure 17.4. The astute reader will notice we have one less step than we did for the AWS example using Glue and Athena. This is because our Azure example will directly reference files on the blob storage when performing the query, as we will see, instead of indexing them into a catalog first, at the cost of having to manually specify a schema in the query. Section 17.3.2 Setting up resources. Before building our DAG, we first need to create the required resources. We'll do so from within the Azure portal, here, which you should be able to access with a proper Azure subscription. In the portal, we'll start by creating a resource group, Figure 17.5, which represents the virtual container of our resources for this use case. Here, we've named the resource group Airflow-Azure, but in principle, this can be anything you want. After setting up the resource group, we can start creating an Azure Synapse workspace, which is currently named Azure Synapse Analytics, Workspaces Preview, in the Azure portal. To create a Synapse workspace, open the page of the service in the portal and click Create Synapse Workspace. On the first page of the Creation Wizard, Figure 17.6, select the previously created resource group and enter a name for your Synapse workspace. Under the storage options, make sure to create a new storage account and file system. Choose any names you like. On the next page of the wizard, Figure 17.7, we have the option to specify a username and password for the SQL administrator account. Enter whatever you like, but remember what you filled in. We'll need these details when building our DAG. On the third page, Figure 17.8, you also have the option of restricting network access by deselecting Allow Connections from all IP addresses. But don't forget to add your personal IP address to the firewall exemptions if you deselect this option. Click Review plus Create to start creating the workspace. Now that we have our Synapse workspace and corresponding storage account, we can start creating the containers, a kind of subfolder, that will hold our ratings and rankings data in the blob storage. To do so, open the storage account. If you lost it, you should be able to find it back in your resource group. Go to the Overview page and click Containers. On the Containers page, Figure 17.9, create two new containers, Ratings and Rankings, by clicking Plus Container and entering the corresponding container name. Finally, to ensure we can access our storage account from Airflow, we need to obtain an access key and secret. To get these credentials, click Access Keys in the left panel of the page, Figure 17.10. Write down the storage account name and one of the two keys, which we'll pass as connection details to Airflow when implementing our DAG. Section 17.3.3, Building the DAG. Now that we have all of the required resources, we can start building our DAG. For the first of two steps, we need to implement an operation that fetches data from our Ratings API and uploads them to Azure Blob Storage. The easiest way to implement this is to combine the Python operator with the WASB hook from the Microsoft Azure Provider Package. This combination allows us to fetch the ratings using our own functions and then upload the results to Azure Blob Storage using the hook. The WASB hook requires a connection ID that specifies which to use for connecting to the storage account. This connection can be created in Airflow using the credentials we obtained in the previous section, using the account name as the login and the account key as password, figure 17.11. The code is pretty straightforward. We fetch the ratings, write them to a temporary file, and upload the temporary file to the ratings container using the WASB hook. For the second step, we need an operator that can connect to Azure Synapse, execute a query that generates our rankings, and write the results to the rankings container in our storage account. Although no Airflow hook or operator provides this kind of functionality, we can use the ODBC hook from the ODBC provider package to connect to Synapse over an ODBC connection. This hook then allows us to perform the query and retrieve the results, which we can then write to Azure Blob Storage using the WASB hook. Footnote 3. Can be installed in Airflow 2 using the Apache-Airflow-Providers-ODBC provider package, or in Airflow 1.10 using the backport package, Apache-Airflow-Backport-Providers-ODBC. The actual ranking will be performed by the Synapse SQL query in listing 17.2. In this SQL query, the OpenRowSet statement tells Synapse to load the required dataset from our storage account, referenced by the URL, and that the data files are in a CSV file format. Following OpenRowSet, the with statement tells Synapse what schema to use for data read from the external dataset, so that we can ensure the data columns have the correct types. Finally, the where statement uses the different parts of the file paths to ensure we only read data up to the current month, while the rest of the statement performs our actual ranking, using the select AVG, group by, and order by statements. Note: in this case, Synapse has access to the storage account because we placed our files in the storage account coupled to the Synapse workspace. If you were to place the files in another storage account, not directly coupled to the workspace, you need to make sure to either grant your Synapse workspace's identity access to the corresponding account or register it with the proper access credentials as an external data store in the workspace. We can execute this query using the following function, which executes the query using the ODBC hook, converts the rows in the result to a pandas data frame, and then uploads the contents of that data frame to the blob storage using the WASB hook. Footnote 4. Note that this requires the proper ODBC drivers to be installed. This driver should already be installed in our Docker image. If you're not using our image, more details on how to install the drivers yourself are available on the Microsoft website. Make sure to use the proper version for your operating system. Similar to the previous step, we can execute this function using the Python operator, passing in the required connection references and container paths as arguments to the operator. Of course, we still need to provide the details for the ODBC connection to Airflow, figure 17.12. You can find the host URL for your Synapse instance in the overview page of the Synapse workspace in the Azure portal under SQL On-Demand Endpoint. On-Demand, on-demand equals serverless SQL. For the database schema, we'll simply use the default database, master. Finally, for the user login password, we can use the username and password we provided for our admin user when we created the workspace. Of course, we only use the admin account here for the purpose of this demonstration. In a more realistic setting, we recommend creating a separate SQL user with the required permissions and using that user to connect to Synapse. All that remains is to combine these two operators into a DAG, which we'll run on a monthly interval to generate monthly movie rankings. With everything complete, we should finally be able to run our DAG in Airflow. If all goes well, we should see our tasks loading data from the Ratings API and processing them in Synapse, figure 17.13. If you run into any problems, make sure that the paths to the data and the access credentials for Azure Blob Storage and Synapse are correct. Section 17.3.4. Cleaning up. After you're done with playing around with this example in Azure Synapse, you can remove all the created resources by deleting the resource group we created in the beginning of the use case, as this should contain all those resources. To do this, open the Overview page of the resource group in the Azure portal and click Delete Resource Group, figure 17.14. Confirm the deletion to start deleting all the underlying resources. Summary. Airflow can be deployed in Azure using services such as ACI and App Service for running the scheduler and web server processes, Azure File Blob Storages for storing files, and Azure SQL Database for the Airflow Metastore. Airflow provides several Azure-specific hooks and operators that allow you to integrate with different services with the Azure Cloud Platform. Some Azure services can be accessed using generalized hooks, such as the ODBC hook, if they conform to these standardized protocols. Using Azure-specific hooks and operators generally also requires you to configure the required resources and access permissions in Azure and Airflow so that Airflow is allowed to perform the required operations. Chapter 18, Airflow in GCP. This chapter covers designing a deployment strategy for GCP, an overview of several GCP-specific hooks and operators, demonstrating how to use GCP-specific hooks and operators. The last major cloud provider, Google Cloud Platform, GCP, is actually the best supported cloud platform in terms of the number of hooks and operators. Almost all Google services can be controlled with Airflow. In this chapter, we'll dive into setting up Airflow on GCP, section 18.1, operators and hooks for GCP services, section 18.2, and the same use case as demonstrated on AWS and Azure applied to GCP, section 18.3. We must also note that GCP features a managed Airflow service named Cloud Composer, which is mentioned in more detail in section 15.3.2. This chapter covers a DIY Airflow setup on GCP, not Cloud Composer. Section 18.1, Deploying Airflow in GCP. GCP provides various services for running software. There is no one-size-fits-all approach, which is why Google and all other cloud vendors provide different services for running software. Section 18.1.1, Picking Services. These services can be mapped on a scale ranging from fully self-managed with the most flexibility to managed completely by GCP with no maintenance required, figure 18.1. On the left-hand side, we have Compute Engine, which gives you a virtual machine to run any piece of software you desire. Compute Engine provides you complete freedom and control, which can be positive, but it also requires you to manage and configure the virtual machine yourself. For example, if traffic to a service you're running on Compute Engine increases, it is up to you to scale vertically by creating a new VM with a larger instance type, or scale horizontally by configuring an auto-scaling policy to create more of the same instances. On the right-hand side, we have Cloud Functions, to which you can provide a function in one of the supported languages, Node.js, Python, Go, and Java at the time of writing. For example, a Python function that returns the current time in a given time zone. So, if you call the function with an argument, CEST, the function will return the time for the CEST time zone. Functions handle small workloads and operate event-based. Google manages your function, that is, the underlying infrastructure, and will scale the number of deployed functions automatically. If a high load is requested from your function, Google will automatically scale up. Google handles all logging, monitoring, and the like. You only have to provide the function. If your use case fits the characteristics of a function, it can greatly improve your productivity. It is not trivial to set up Airflow because of the shared storage it requires for storing and sharing DAG files. Mostly applies when running Celery Executor or Kubernetes Executor. This limits our options in GCP. Cloud Functions serve stateless event-based functions, which Airflow is not, and therefore cannot be deployed on Cloud Functions. Running Airflow on App Engine might be technically possible, but with a few caveats. App Engine expects a single Docker container, while the minimum Airflow installation is already split between a web server and a scheduler process. This poses a challenge. Typically, applications that expose something, for example, a front-end or REST API, are run on App Engine, which scales automatically based on the load. Airflow does not fit this model, as it's a distributed application by default. The web server could be a good candidate, though, to run on GAE. The Airflow scheduler does not fit the App Engine model, so this leaves us with two options, GCE and GKE. Kubernetes was already discussed in detail in Chapter 10. The Kubernetes engine is a good fit for Airflow. Helm charts for deploying Airflow on Kubernetes are available. Plus, it provides abstractions for mounting file systems shared by multiple pods. The Compute engine gives you complete freedom to run and configure your instance. We can distinguish two flavors of the Compute engine, a Linux-based VM and a container-optimized OS, COS, VM. A COS system is ideal for running Docker containers and therefore seems attractive from a deployment perspective, but unfortunately poses an issue in combination with Airflow. Airflow requires a file system for DAG storage, potentially shared between multiple machines, for which storage accessible via NFS is a common solution. However, COS does not come with NFS libraries. While it might be technically possible to install these, it is not a simple task. So it's easier to switch to a Linux-based VM, which gives complete control. For a shared file system, 2 out of the many options on GCP are as follows. Google Cloud File Store, a CGP-managed NAS service. GCS mounted with Fuse. Shared file systems have long been a challenge, and each comes with pros and cons. If possible, we prefer avoiding Fuse file systems, as they apply a file system-like interface over something that was never intended to be a file system. For example, GCS is an object store, which comes with poor performance and consistency challenges, especially when used by multiple clients. For other Airflow components, the number of options is less and thus easier. For the Metastore, GCP provides Cloud SQL, which can run both MySQL and